Good morning students, welcome back to online class. Today we are going to study about the Lewis structure, Lewis dot as well as limitation of the Lewis theory. So let's start about the formal charges. Now what is formal charge? Formal charge can be defined as the difference between the valence electron of the atom is in an isolated or free state and the number of electrons assigned to that atom in the Lewis structure. So the formula for calculating the formal charge is what? That formal charge on an atom is equals to total number of electron in free atom minus total number of non-bonding, that is lone pair electron, minus half of total number of bonding, that is shared pair electron. Now you understood the formula. What is that? Total number of electron in free atom, total free atom minus lone pair minus half of the shared pair electron. This is the for finding the formula for the formal charge of the electron of an atom. So this is an example of the ozone molecule, that is O3. Unpaired, this one is a 1, 2, 3 we can take. This is the unpaired, this is the shared electron, right? This is the lone pair. Let's start. Here is the example of the ozone molecule. The formal charge on the first or central oxygen atom means this one. So total number of the valence electron in the free atom, this is a free, this one we are talking about. So total number of valence electron is 1, 2, 3, 4, 5 and 6. So 6, oxygen is having outermost orbit 6 electron, right? So 6 is, no need to count, minus non-bonding electron, this is the non-bonding electron, that is 2. So minus half of total number of bonding electrons. Bonding electrons, how many pair bond is there? 3 bond is there, and bonding electron 1, 2, 3, 4, 5, 6, right? So there is 6. So 2, 3 are 6, minus 2, minus 3. So the formal charge for the central oxygen atom is +1. Understood? Now we'll take the second oxygen atom. Here total number of the valence electron is 6 minus non-bonding electron. How many non-bonding electron is there here? Non-bonding. So the non-bonding charge on the electron, here this is the third one, sorry. This is the second one. Non-bonding electron is 1, 2, 3, 4. So 4 and half. Total number of bonding electrons in this oxygen. This is the second oxygen. So 1, 2, 3 and 4. So 4. So the formal charge on the second oxygen atom is 0. So here no plus, no minus is there, only 0 is there. Understood? Now formal charge on the third oxygen atom is, this one is the third oxygen, this is the first one, this is the second one and this one is the third one. So here the total number of valence electron is 6. Total number of non-bonding electron is 1, 2, 3, 4, 5, 6. See here, right? 6 and half of bonding electrons. How many bonding electrons is 1 and 2? 2 bonding electrons. This is the bond, and for this bonding electron is 2. Understood now? So here the formal charge 2 cut, minus 1 will be there. So minus 6 minus 1 minus 7. 6 minus 7 is minus 1. So the formal charge of the third oxygen atom is minus 1. Now this is the formal charge. Now you understood how to calculate the formal charge of any atom. Now, what is the limitation of the octet rule? The incomplete octet of the central atom. This is the center in this BeH2. What is the central atom? Beryllium is a central atom, right? So this is the beryllium. This is central atom. This is especially in the case of the element having less than 4 valence electron. Here you are having less than 4 electrons atom. That is outermost orbit is 2 over here. So this is the incomplete octet rule, because in this beryllium only 1, 2, 3, 4 is fulfilling. The outermost orbit is not 8. So this is the one limitation of the octet rule, that the compound is not surrounding by the 8 electrons. Second is what? That is not applicable for the molecule in which central atom has less than 8 electrons, that is contracted octet. See, this is the contracted octet. Why? Because it is having only 4 electrons, not completing the octet rule over here. See here, there are some examples that does not possess the octet rule, like lithium chloride, only 2 electrons is there. Boron trifluoride, 1, 2, 3, 4, 5, 6. 6 electrons are there. Central atom. Boron trichloride, here also 6 electron is there. Beryllium chloride, 4 electron, and aluminum is the central atom. Now aluminum chloride, that is 6 electrons are there. So they are not fulfilling the 8 electrons. So this is what the limitation of the Lewis theory. Okay. The odd electron molecule, in molecule with an odd number of electrons like nitric oxide, that is NO, and nitrogen dioxide, that is NO2, the octet rule is not satisfied for all the atoms. See here is example of chlorine and oxygen they have taken. So it is not fulfilling the 8 electrons. The expanded octet is what? See here, this is a PCl5, phosphorus pentachloride. The element in and beyond the third period of the periodic table have apart from 3s and 3p orbital. 3d orbital also available for bonding. In a number of compounds of these elements, there are more than 8 valence electrons around the central atom. But this term is expanded as a expanded octet. Yeah. Next, here is some other compound like sulfur dichloride, SCl2. S has an octet of the electron around it. See here, how many electrons are there? 1, 2, 3, 4, 5, 6, and 7 and 8. So this fulfills the octet rule. So there are some limitations of the octet rule, that it is clear that octet rule is based upon the chemical inertness of noble gas. However, some noble gases, for example xenon and krypton, also combine with oxygen and fluorine to form a number of compounds like HCF2, KrF2, HCOF2. This is what? This is the all noble gases which combine with the oxygen and fluorine. So this theory does not account for the shape of the molecule, and it does not explain the relative stability of the molecule. That is being totally silent about the energy of the molecule. There are some limitations of the octet rule. Here is the ionic or the electrocovalent bond. From the causal and the Lewis treatment of the formation of an ionic bond, it follows that the formation of ionic compound would primarily depend upon the ease of the formation of the positive and the negative ion from the respective neutral atoms, and the arrangement of the positive and the negative ion in the solid, that is lattice of the crystalline compound. So here, what is the ionic bond or electrocovalent bond? Ionic bond means what? Donating and accepting the electrons. For example, sodium, the outermost orbit is 1, like 281. This is the electronic configuration. So 1 is the outermost orbit. So that is having a tendency to donate the electron. And chlorine is the outermost orbit is 287. That is 7 is the outermost orbit. So it has tendency to accept the electron. So the element which is having a tendency to donate and accept, that bond is called ionic bonding. See here, they have taken example of metal, gives metal plus electrons. Understood? See here, intake any +1, X plus electrons gives X minus over here. So this is the formation of the positive ions. How it was 281 and 1 electron is donating. So as it is donating, it's a plus, positive ion is there. Because it is donating, donor is always positive. Acceptor is always negative. So here the element atom is there, it is accepting the electron. So accepting the electron means negative ions is there. Okay. So the one positive and negative will attract with each other and form a compound, that is NaCl. Right? The electron gain enthalpy. This is a symbol of electron gain enthalpy, EGH. is the enthalpy change when a gas phase atom is in the ground state, gains an electron in the electron gain process, and the process may be exothermic or the endothermic reactions. So the ionic bond will be formed more easily between the element with comparatively low ionization enthalpy and element with a comparatively high negative value of the electron gain enthalpy. So we will study about the ionization enthalpy and the electron gain enthalpy. What is the electron gain enthalpy? When there is a accepting the electron, so it is an electron gain enthalpy. Okay, so in ionic compound, the sum of the electron gain enthalpy and the ionization enthalpy may be positive. Obviously, the ionic solid of the gain enthalpy and the ionization enthalpy may be positive, but still the crystal structure gets stabilized due to the energy released in the formation of the crystal. So the energy will be released for doing this process. It may be an exothermic reaction or endothermic reaction. See here the example of Na plus. The formation of Na is 495.8 kilojoule per mole, while the electron gain enthalpy for the change of the chlorine, that is Cl in a gas form plus electron is Cl minus, is what? 348.7 kilojoule per only. So this is more and this is less. So here the sum of the two is 147.1. It is minus minus 348.7. So when you add this one, it is 147.1 kilojoule, which is more compensated for by the enthalpy of lattice formation NaCl, that is minus 788 kilojoule per mole. So this is the energy. You don't need to learn about the energy, enthalpy, and this one marking the numbers. So just for the understanding, it is the example is taken over here. Therefore, the energy released in this process is more than the energy absorbed. So wherever you can get the negative one, it's an exothermic reaction, and the positive one is a endothermic reaction. Now, what is lattice enthalpy? Lattice structure means what? A complete crystal form of the NaCl or any ionic compound. So the lattice enthalpy of an ionic solid is defined as the energy required to completely separate 1 mole of a solid ionic compound into gaseous constituent ions. That is the lattice enthalpy. What is the enthalpy? Enthalpy is energy required by the compound which is converted to the gaseous constituents. For example, NaCl is lattice enthalpy is 788 kilojoule. This means this much energy is required to separate 1 mole of solid NaCl into 1 mole of Na plus in a gaseous form and 1 mole of Cl minus in a gaseous form to an infinity distance, that is a gaseous form. So this much energy is required to convert it. It's a lattice enthalpy. Now we'll discuss about the bond parameter, and the bond parameter is divided into bond length. So what is a bond length? Bond length is defined as the equilibrium distance within the nuclei of a two bonded atom in a molecule. So in the case of the covalent bond, the contribution from each atom is called covalent radius of the atom. So see here, this is the molecule of hydrogen or chlorine. Take any example. So the distance between, this is the covalent radius. So bond length divided by 2. That is the covalent radius. Where is the radius? So see, this one radius is different and this radius is different because it is totally overlapped with the two atom overlapped. We'll say overlap. Okay. So how to find the covalent radius? So bond length, this is the bond length divided by 2. That is, this one is a covalent radius. Okay. So bond parameter is divided into 4 terms, that is bond length, bond order, bond angle, and bond enthalpy. So and where it is bond length is used, it is used in the spectroscopy. It is used in the X-ray diffraction where the molecules can be seen over here, and the electron diffraction also. Okay. So the covalent radius is half of the distance between the two similar atoms joined by the covalent bond. Understood? What is the covalent radii? Half of the distance between the two similar atoms. If there is a two similar atom, then there is a half of that one, and covalent bond of the same molecule. The van der Waals radius represents the overall size of the atom. 1 atom size will be different, the other atom size will be different, then it is a different covalent radius will be there. So the van der Waals radius represent the overall size of an atom, which includes its valence shell in the non-bonded situation. So see here, there is a 3 different structures is given, the one single bond, double bond and the triple bond, and see the number of bond will be there, the bond length is decreasing. See here, one single bond, so bond length is more. In the double bond, the bond length is less, and in the triple bond, the bond length is very less, that is 1.54, 1.33 and 1.20 Armstrong. This is the ethane, ethyne and acetylene. Ethylene also you can say. So now about the bond order. If this is the bond order, how many bond? 1 bond. How many bond? 2 bond. How many bond? 3 bond. So this is the bond order. So from the bond we can able to understand whether it is saturated or unsaturated. What is saturated? So in this is the triple bond. In that only one bond is strong, the other 2 bond is weak, that is a pi bond we can say, and one bond is strong, that is a sigma bond. Okay, sigma bond and pi bond is there. Here in the 2 bonds, one is a sigma bond and one is a pi bond. So one which is pi bond, that is weak, so we can break it easily. Okay. Now about the bond angle, this we can call as a bond angle. This is the symbol molecule structure of a water, H2O. So it is defined as the angle between the orbital. This is the orbital, the angle between the orbital, the bond OH and OH bond, and that bond angle, this is called as a bond angle. It gives some idea regarding the distribution of the orbital around the central atom or in the molecule. So what is the central atom in this molecule? Oxygen is in the central atom. Okay. So see here the bond angle. This is which shape? Square, planar shape. This is the linear shape, or we can say this one is the octahedral shape. This one is a triangular planar shape. And this angle is having a 90-degree octahedral, always 90-degree linear, 180, this you know very well. In the triangular planar, the bond angle between the 2 bond length is 120 degree. See here, this is the figure of the methane, CH4. So the bond angle between the methane is 109.28. This you need to remember. Now as we have studied what is enthalpy, that is energy required to break down one molecule, is a bond enthalpy. So see here, we have discussed right now, this is the hydrogen, and energy required to break down the molecule is 435.8. So this much energy is required to break down. So H2 in a gas form with the enthalpy energy taken, it produce hydrogen in a gas form. See here, so this is the enthalpy, bond enthalpy for the methane gas. So how much energy is required to break down this one? So first CH4, on applying the bond enthalpy, it gives hydrogen is taken out. So the first energy it is taken 435 kilojoule per mole, and what is remaining? CH3 is remaining, and from that CH3 one hydrogen is taken out, so CH2 is remaining. So for that 444 kilojoule is utilized, and again from the CH2 H is taken out, so CH is remaining. Again 440 kilojoule per mole is used for as energy, and from this CH carbon is different and all hydrogen is different. So at last 343 kilojoule per mole energy is used. Now what is the average for energy is used for breaking methane gas? That is CH4 gives C plus 4H plus is 1662 divided by 4. This is the average bond enthalpy. What we have to do? Add this one, divide by 4. Then you will get total energy. Average energy is required is 415.5 kilojoule per mole. Now clearly understood about bond enthalpy, bond angle, bond order and bond length. Thank you. Hope you understood the topic very well.